Okay, let's get back to class. So we have been talking about this kind of optimal prefix code and this corresponding full binary tree. So the first observation we make is that as long as basically the frequency, maybe for instance here, I mean the in the corresponding optimal prefix code, I mean if the depth of U is smaller than depth of V, then the corresponding letters on those should satisfy this kind of frequency relationship is Fy is larger than or equals to Fz. Otherwise, you can just like switch them and you can get like a smaller ABL. So I guess this is a relatively straightforward observation. So another thing that we can make, I mean, in general, we think about like basically for this ABL, what is the expensive part of this? So basically the expensive part is that the ABL, it really suffers from nodes with largest depth. I mean, in general, about like large depth. So the next observation we are going to make is we are going to make a specific observation about like the nodes with largest depth. So observation 2. So let's consider a leaf V in T prime. The largest depth among all the leaves. I mean, we talk about the largest step, it should always be a leaf. I mean, if it's not a leaf, I mean, if it's not a leaf, it has like children. I mean, the children has like even deeper depth. So of course, I mean, the largest steps among leaves is also the largest steps among all the nodes. So leaf V as a parent, U and T prime. Because we have the assumption that we have a full binary tree. And T prime being a full binary tree implies that U has another child, W. Then W is a leaf. Interesting. I guess this is simply apparent. I mean, we are talking about a V here. The V here is like of the largest depth. And basically, the V here has a parent, which is called U here. So we want to rule out the possibility. I mean, because the binary tree here we studied is a full binary tree. I mean, basically the U here, it must have another child, which is this W that we studied here. So maybe let's actually move this step here. But if the W here, if it's not a leaf, then basically suggesting that it further has maybe on like a children along this. It's just well as the definition that the V here has the largest depth. So basically, that's the reason why here it is basically for this W here should always be a leaf here. I guess this should be relatively straightforward. Any question? Okay, so this is something quite straightforward, and I guess we want to make some further observation. So this is also one sentence that we can very easily see. That is basically the order in which we assign letters in the same level to the leaves with the same does not influence ABL. I guess this is just directly straightforward by the definition of ABL here. Because if the depth is the same, I mean, it's just like the summation of all the frequency of the same depth. I mean, even if you switch the corresponding code, it does not influence that. So I guess it's basically three very direct observations, but something we can give observation is that we can basically do this kind of things. So basically based on the observations above. Sorry. Without loss of generality, we can assign V and W to get the two lowest frequency letters of all. I mean, this V and W is just like the V and W we draw in this graph. So let's think about the implication here. I mean, we talk about the V here to be of the largest depth. I mean, basically, if the V here is I mean, if we on the other hand, we consider the letter with the smallest frequency. If it is not at the very lowest level, then basically we can make a switch between the corresponding letter currently on V and on that letter. So that is actually going to make the ABL smaller, and this actually contradicts with the fact we are talking about optimal prefix code. So basically, we are pretty sure that for the smallest, I mean, basically for the V and W, they should be on the very lowest level of this full binary tree. And basically, as we mentioned in this observation 3 here, it does not matter if we make a switch accordingly. So basically, we can just feel free without loss of generality to assume that V and W here to be actually the two smallest, I mean, the two letters with the lowest frequency. So it's just like a direct result that we can obtain here. And typically, we can call this safe to lock them together. And we just call them as the lock them together property. So is this clear to you? So basically, I think after we have you make some observations, we are really having a better understanding about like the deepest side. And actually, this suggests some algorithm. So in particular, this suggests us. So basically, replace. Basically, we replace V and W by like matter letter. I mean, obtaining an alphabet smaller by 1. And call this recursively. So this is basically the part we are making the greedy strategy. That basically we have been taking a close look of this full binary tree for this optimal prefix code. And basically without loss of generality, we have this V and W of lowest frequency to be at the bottom. And actually they're siblings. I mean, they have the same parent and they are the deepest in this binary tree. So we just like combine them together, and by doing this, we just shrink the size of the alphabet by 1. And basically we can call this recursively and again and again. So basically, this is the algorithm that we are actually going to talk about today. So this is basically the Huffman's algorithm. So for this Huffman's algorithm, the input is basically an alphabet. Sorry. An alphabet S, and also a frequency fx of sequence. And the output is basically a full binary tree as a prefix code for S. So let's write down the algorithm. So it's basically something like this. So if, I mean, S has 2 letters, I mean, this is just a very simple. We just like encode one letter being 0 and the other being 1. And I guess it is important that we deal with the else case. In general, the alphabet S is large. So we let Y star and Z star to be the two lowest frequency. To be the two lowest frequency letters. So basically, according to this idea of Huffman's algorithm, basically we want to form a new alphabet. Let's call this S prime by deleting Y star and Z star and basically replacing them with a new letter. Let's say W of frequency. Because we are actually doing this as a meta letter and we just like combine them together. So of course the frequency makes sense to have them to be Fy star plus Fz star. You just plus them together. And then we recursively call Huffman's algorithm. With our input S prime, basically in this new alphabet. And let's say that the output, the binary tree that it obtained is maybe like a T star. So basically, using this recursive call of the Huffman's algorithm, we can define a prefix code of S as follows. So basically, by the previous call, we have this T prime, basically start with T prime, and then we take the leaf labeled. Because we have basically for this recursive, we call this Huffman's algorithm. Basically, we make some kind of decoding. Basically, we in this letter has size of S the cardinality of S minus 1. So basically, we need to somehow restore this W because the W is not in the original alphabet. So basically, we need to restore this W to be the Y star and Z star. So basically, we just take the label leaf label W and add two children below it labeled Y star and Z star. I guess this makes sense because we have combined Y star and Z star to be a meta letter and you just merge them. So it makes sense that if you do this restore procedure, you just like remove this W and then basically attach two children below it and call it actually a Y star and Z star. So let me actually finish. Yes. So basically, this is the Huffman's algorithm. So any question about the statement of Huffman's algorithm? So I think the intuition is clear, but maybe let's nevertheless run an example on this. So let's just consider the very beginning example that we have been talking about. That's Fa equals to 0.32, then maybe Fb 0.25, Fc 0.20, Fd 0.18, Fe 0.05. So let's, for instance, consider this. So let's just run the Huffman's algorithm for this. So the first step is that we merge D and E into a single letter. And this is basically the letter of D. Now we just write this a bracket to represent this is a meta letter of frequency. So basically 0.18 plus 0.05 equals to 0.23. Basically have this. And like the new alphabet is going to be FA, still this, FB, still this, FC, still this. But we are actually, sorry. Yeah, I think I'm correct here. Sorry, but actually, let's move this. Because we noticed that FDE here is actually here is actually 0.23, which is larger than FC here. So maybe let's just for our convenience, let's just write in this. So this is basically the first step of running Huffman's algorithm. So next, we merge DE and C into a single letter. Let's just, for instance, call this as a CDE here. Of frequency plus them together. So 0.23 is 0.20 to 0.43. So basically now we have CDE equals to this, and then we have the FA and FB here. So how about next? So next step is that we are going to then, because in the current case, it is A and B, they have the lowest frequency. So we just merge A and B into a single letter. And let's call this AB of frequency. Plus them together. So now we have basically FAB goes to 0.57 and also F of CDE equals to 0.43. And finally, because we have discussed that if we have two letters, we can just feel free to assign AB to 1 and say CDE to 0. So how does this look in the form of a full binary tree here? I guess you can look maybe from like a top-down perspective. So at the very beginning, we have this set S here. So let's look at the last step. The last step here, we assign AB and CDE here to 1 and 0 specifically. So we actually have this. Should be like an AB here, and here we have like a CD. And then we look at the second to last step, which is step 3 here. So basically, we have merged A and B to the letter AB here. So let's, for instance, let's write like A here and B here. So here we use a relative. I mean, there are. I mean, as we just discussed in the observation 3 here. I mean, basically in the same level, it does not make a difference between like whether you mark them by the by which. I mean, like according to the order of 0 and 1. But here, I guess for the sake of concise, I mean, basically to make everything simple, we just like. I mean, each time which one is larger, we just make it to be 1 and the smaller one to be 0 here. So basically, that's the reason here on AB here, we just for convenience can write this. We make this to the right, and basically we make CDE to the left. And here, basically in this level, we actually make A to the right and B to the left. And this is just for the sake of making everything look good. And basically, after looking back along this, I mean, the fourth step, the third step, and we are now looking at the second step. For the second step here, here we actually merge DE and C here, and actually the frequency of DE is larger than the frequency of C. So maybe let's, for instance, write a DE here, and actually let's write a C here. And finally, here we are going to have a D here, and finally we are going to have an E here. So as we just mentioned, without loss of generality, if we have two siblings, we just have the larger one with 1, a smaller one with 0. So basically in this in this full binary tree, we basically have A here to be 1, 1, and B here to be 1, 0, and C here to be actually 0, 0, because left, left. And actually D here to be 0, 1, 1, and actually E here to be 0, 1, 0. Okay, so how about this example? Is this example of Huffman's algorithm clear to you? Okay. So let's analyze Huffman's algorithm. So basically, we first prove the correctness. So basically, we establish this optimality. So basically, we prove by induction. Induction on the size of the alphabets. So guess when n equals to 2, this is just trivial because in the case where you have two letters, I mean, the best way is just like one letter is 0 and the other is 1. I guess this is just trivial according to the definition of Huffman's algorithm. So now, assume the correctness for all alphabets with size n minus 1. So let's now maybe for instance we have an alphabet of size n. And let's for instance let's denote T here to be the output of Huffman's algorithm. And I guess we use the previous notation. So basically we denote Y star or Z star in S to be the two lowest frequency letter. Right. So this is just notation. I think because we want to use the induction, so we want to use like one step before. So basically, we can denote T prime to be the output of Huffman's algorithm. Basically, with Y star and Z star merged as letter W. So basically, we look one step before. And now, of course, since we merge, the alphabet size of S prime should equal to n minus 1. Okay, so basically, we want to use the induction to make the proof here. So we want to have a good understanding about what is the ABL of T prime and what is the ABL of T and their corresponding relationship. So one fact that maybe is not very difficult to imagine and we are actually going to prove rigorously is that actually the ABL T prime equals to the ABL of T minus F Y star plus F Z star. Intuitively, it's just because in the T here, the Y star and Z star, they're actually one step further compared to the W in this T prime here. So this is just the intuition. And because recall the definition of the ABL, I mean, we have been talking about this too long. Let's just copy it. Oh, sorry. Let's just copy this here. Let's just for our convenience, copy this here. It's just like the depth of y prime and z prime. They're actually one step further and actually compare a t to t prime, and that is the reason why their difference should be actually be this sum here. This is I guess this intuitively should be relatively easy to understand. So maybe let's just give a very big check. So the ABL of t equals to the summation of x in S fx. It's the depth in t x, and this actually equals to f y star times the depth t y star plus f z star, depth of t of z star, and all the other vertices. X in S x not equals to y star and z star, and fx times the depth. So let's take a close look on this. So we know that basically in our previous observation, we know that y star and z star they have the same depth. So and also we have merged the y star and z star in this tree t prime here. So we can safely say that here it equals to f y star plus f z star times 1 plus the depth of t prime of w. So this is basically the depth t prime of w is actually exactly one smaller than the depth t of y star and also the depth t of z star, specifically due to the definition of Huffman's algorithm. And for all the other vertices, so basically for this summation, I mean, this is irrelevant to the change between t prime and t here. So we can just feel free to write this down. So x is actually because we are making the induction here, we say that as x is inside as prime, and x is not equals to w. Fx times the depth t prime of x. And then we just combine them together. And this equals to fy prime plus fz prime. And actually, we just like for this part, we merged it into the summation there. So and this equals to the summation of x in s prime fx times the depth of t prime x. And actually, this equals to fy prime, fy star plus fz star plus ABL. And this finished. So is this proof clear to you? Any questions? Okay. So now in our induction proof, so I mean, we can give maybe for instance assume the contrary. Then and there exists a full binary tree. Maybe let's say for instance like a full binary tree Z for the alphabet S such that ABL is smaller. So here is basically a place that we want to utilize the structure. And actually the thing we are going to use is basically we want to use this lock them together property. So basically there is such a Z. And basically we can rearrange the labels in this tree Z here that basically we assume in the contrary, and basically we can such that because we know that y prime and z prime they are actually the two lowest letters, so we can make a rearrangement such that y star and z star they're actually siblings and deepest in Z. Okay. So I guess this is relatively straightforward, and basically we want to use the induction to actually attack the kind of to attack the assumption here, and basically we want to get a contradiction. So now we apply a similar strategy of the Huffman's algorithm, but on this presumably assume even smaller the tree Z here with an even smaller ABL. So we attack this, and we by just following the Huffman's algorithm. So we just delete the leaves labeled Y star and Z star from Z, and label their former parent with this W that we have been using throughout. So I guess this is a very natural strategy that we want to consider. And actually, this is a place that we can utilize. Oh, sorry. This is a place where we can utilize our induction, because this basically actually gives you a new tree. And let's call it like a Z prime for S prime. So basically, by the fact above, so basically we use this. We basically use this fact. So basically, by the fact above, we know that the ABL of Z prime is actually going to equal to ABL of Z minus F Y star plus F T star. So together with ABL of Z are smaller than ABL of T, we can actually get that ABL of Z prime is smaller than the ABL of T prime. But this contradicts with our induction assumption. And basically this finishes our proof. Okay, so is the correctness of Huffman's algorithm clear to you? Okay, so I guess we have been basically finishing the proof of the correctness of Huffman's algorithm. And I think the remaining question today is that we want to determine the time complexity of this algorithm, so running time. So what is the running time of this Huffman's algorithm? Maybe you can think briefly about this. It's about this kind of update, this kind of strategy. Right, and actually the Huffman's algorithm can actually be run in O of n log n time. So how do we do this? So basically, we maintain alphabet as basically in this heap we talked about last time. So this is basically a place we want to utilize this very good data structure that we can use. So basically, recall that in heap, insert a node takes O of log n time. And basically, we use each letter's frequency as its key. So basically, I think it is very important that you can observe that in this construction of basically in this Huffman's algorithm, in the construction of this full binary tree. So basically, each time we are extracting the two smallest value. the minimum twice. And basically recall that extract mean actually takes O log n cost. And after that, we need to put something back. So basically we insert a new letter whose key is the sum of these two lowest frequency letters. Okay, so this is basically suggesting that in each iteration, we have two extract plus one insert, which is basically of log n in total. And basically, there are like n minus one iterations until we got the case with two letters, and that takes O1 cost. Okay, so the overall cost, I guess, you can clearly see, cost is basically bounded by n of O log n. It's basically O n log n. So is this time complexity analysis clear to you? Basically this cost of O log n. So basically here, I guess the heap is just that we as we discussed last time, we use the heap to store the frequency of all the letters. And as you can clearly see, the main cause, I mean, in this Huffman's algorithm is that we need to store this corresponding values, and we find the two lowest frequency ones. And we basically we run two times of the extract mean, we take them out, and we compute their sum, and basically we put it back to this heap. But actually, both the extract mean and insert can be maintained in cost of O of log n. And basically, in each iteration, this is this cost, and the overall cost is subsequently going to be this O log n here as a total. Okay, so in general, any question about Huffman's algorithm? Okay, so hopefully this is clear to you, and I guess it's basically the time that we wrap up this this lecture. So basically, in our you can see that in the past lectures, we moved from basic definitions to graphs to more general problems. So in particular, I think today we are talking about interval scheduling. And on the other hand, we also talk about Huffman codes. So basically, I mean, these are like a very basic and very relative, very like a toy example case for a very important direction, for instance, like scheduling and also data compression. And I think you can imagine that as we discussed, scheduling, data compression, etc., they are actually super useful. And I think both from a practical side and also from a theoretical side, people have been developing a lot of algorithms correspondingly. So I want to emphasize again one applications in both theory and practice. So basically so far, and I think basically for this idea we have been talking about is basically a greedy idea. So basically, I think the next we basically introduced the basic definitions and like basic models of graphs. And I think basically we have been talking about like greedy algorithm on graphs, this a Dijkstra's algorithm, Kruskal's algorithm. And I think today we talk about another two very important problems like integral scheduling and Huffman codes. So basically next we will talk about more ideas of design algorithms. So in particular, in the next class, we will talk about an idea called divide and conquer, which is actually going to give you another main idea of designing algorithm and also a fast algorithm for a lot of problems. Okay, so this is basically the lecture today. So do you have any questions about the integral scheduling problem and the Huffman encoding? Basically, the Huffman codes and this for this optimal prefix codes problem. Okay, so if there's any questions, so this is the end of this lecture and see you next week. Also, and also very importantly, because of the holiday changes, although the next lecture is actually the beginning of October, but we are actually having a lecture. We actually skipped the National Day break. But on the other hand, we will have the semester will actually finish 1 week ahead. So just keep in mind there is a lecture next week. Okay, see you then.